So the next moonshot that we will cover is the trustworthy data. It will be covered by Joaquin Vanschoren. And trustworthy data is actually about developing technologies and protocols to safely store and process data in a responsible and ethical way. Joaquin is an assistant professor at the TU. His research focuses on the automation of machine learning and meta-learning. He co-authored the book Automatic Machine Methods, Systems, Challenges, published over 100 articles on these topics, and received multiple awards for his work. He aims to build AI systems that learn how to learn, progressively moving from hand-designed algorithms to learned algorithms that optimally build on prior experience and efficiently adapt to new tasks. Also, a fun fact is that Joaquin has 3 small children who constantly remind him that humans learn really different than a machine does. The small children play, they invent their own games, and are constantly preparing themselves for the future. AI doesn't do that well yet. And for him, this was an observation that there's still a lot to do in this field of expertise. So welcome to the stage, Joaquin.
Thank you.
Yes.
Thank you. I'm Joaquin Vanschoren, assistant professor at TU. And today I'd like to talk to you about the work that me, my colleagues, and people all around the world are doing on opening up and automating machine learning. To start with a success story that's very recent, so DeepMind recently solved protein folding using AlphaFold. So this, the task here is that you're given, you're given a protein sequence, basically a sequence of amino acids in a large molecule. And from that, you have to predict how they fold. And if you can predict that, then you can accurately help solve diseases. And that's a very hard task that people have been trying to solve for over 40 years. And they did this by building a machine learning model. So it's a deep learning model that basically maps information about the sequences to the structure and the torsion of individual amino acids. Right? And if you can do that, then you can solve all these problems. You want to, I should quantify this, that such things are only possible if you have good and accessible data to work with. And in this case, there was a lot of data already gathered by the community. You also need a very clear goal, a clear metric that you want to optimize towards. And you need a team of really smart people, typically a very large team of smart people to do this. Now, the question I want to answer today, or think about today, is can we do this on a large scale? Can we go from AI-ready data, give it to a bunch of smart people, and come to solutions? Now, AI-ready data is a bit vague. So what I mean with that is that the data is well organized, it's easily accessible, it's uniformly formatted, and it has consistent metadata, so you know what you're dealing with. And the solution should have a clear goal and should be reproducible. Now, to really democratize this, the bottleneck is often this team of smart people. And what we want to think about is how can we facilitate this by automated AI tools? Can we allow smaller groups of people to solve hard challenges by giving them assistance with AI tools? Okay, how? So as an inspiration for this work, we looked at astronomy. There's this great telescope. It's called Apache Point. It's in New Mexico, in the US. And all it does is it scans the sky every night, and gradually it builds a map of the whole universe. Slow work, but over time they build more and more data. And this had immense impact in astronomy. The way they did this is, first of all, you have one telescope, it takes images, and then the smart thing is they automatically pushed all the data online. So they have a well-organized map of the universe that anybody in the world can access. So you can point any point in the sky, see what's there. And you can use and combine the data in different ways. And what that allowed was that many people started to use machine learning to sift through all this information and make many new discoveries. And over the years, thousands of papers came out this way. And research was sped up tenfold because instead of spending years doing something, you could let an algorithm find answers much faster. It's expanded, and now it's a global system, and telescopes all over the world send data there. And there's even an interesting citizen science project where even citizens made new discoveries while looking through this data. So how can we generalize this idea towards other types of sciences, for instance, and also business applications? So the question I want to answer is, what if we could organize all the world's machine learning information and make it universally accessible and useful? So the last part is the same, right? So let's start with a well-organized repository of data. How do we get there? Once we get there, then we can easily run many algorithms and come to new discoveries. But how do we get there first? Right? Oftentimes, data comes in various forms, different sources, different formats, and so on. So first of all, we need to organize this information into one whole that's easily accessible and organized. So we started thinking about this, how can you solve such a hard problem? And we started thinking about how machine learning professionals and researchers actually do this. And oftentimes, they basically first take the data and they build some kind of a data frame or matrix or a record of all the information, some structured representation of the data. Why? Because almost all machine learning models require you to first build basically data frame, and then only then can you build machine learning models. So people are already doing this. So what if we start from there? Let experts do what they always do, but then we provide them an API that from this data frame lets them automatically organize it into a central place. An API is just a way to send data across the internet. Right? And this is a smart API. It also semi-automatically looks for problems with the data, it extracts metadata, it converts data into uniform formats, and it can do that because we have quite standardized ways of handling with this data. Then the expert also has to provide a task. That's what do you want to do with the data, like classification, regression, predicting something, and also describe that in the same way. Now we have a repository online which has data and clear tasks. Okay? Now the next question, okay, how do I give that data to machine learning algorithms? Right? And so then for them, we have an API that will take the data, build it into trained test sets, train models with it, fully integrated in tools like scikit-learn and TensorFlow and Torch. Let them build models, and when they're done, they can share those back through the same API. And now we have one repository where we have data, we have tasks, we have the algorithms, and we have the solutions, or how well these models work, all organized in one whole. And then we can also give that data back to anybody who wants, can use the same APIs to access all this information. And this means that anybody in the world can go there, find very well-defined machine learning problems, and see exactly what works and what doesn't. So this repository is called OpenML, for Open Machine Learning. And you can access it through the APIs from anywhere you want. There's also a web interface you can go to for people who don't regularly program, and they can also do most of the things there as well. Just to give you a quick preview of the website, so what we have, this is the website. You can browse all the data sets and tasks and flows there. Here you have, doesn't work. Okay, here you have a search box, and you can search some data sets. In this case, I searched for some data about trees from satellite data, and then it automatically builds a representation of the data set so you know what it's about. You can also then look for tasks. For instance, this is a classification task, and so here are different tasks. Here you can see all different algorithms that were built. So people build these algorithms with scikit-learn, with R, with TensorFlow, and so on. And on the right, every dot here is a model, and you can see how well all these models work. So just by going online, you can find a problem you're interested in. You can see what works and what doesn't work. And you can click on these buttons, on these dots, and download the models and use them. You can also, of course, do this through APIs. And this is the way we typically do it, because this allows us to automate a lot of our work. Right? So before, we had to spend a lot of time writing scripts, processing data, building models, getting them back. But having these APIs now allows us to do this very, very efficiently. So you can have one person who has an interesting data set. You can just publish it. Somebody else can then find that that's interesting, download it with the task information, build models using any tool they want, and then share them back to the platform. If you're a coder, this is what it looks like. It's just 4 lines of code. The first builds a model using any tool you want. The second downloads the data and the task. Then the third line basically runs these models, evaluates them in a systematic way, and the final line just publishes them and pushes the results back online. So with these 4 lines of code, you can download data, build models, and share them with the world. OpenML has grown into a large community. We currently have about 250,000 yearly users. We have about 30,000 people who are also registered on the platform who can contribute information, and it's been referenced in over 700 publications. And currently we have about 20,000 data sets, 8,000 flows, algorithms, and 10 million runs, experiments. Okay, that's great. So now we have an organized repository of data and problems. Now we have this. Can we also tackle the second part? Can we automate the building and the creation of these machine learning models? Okay, and so why is this an interesting problem? Well, because machine learning is very labor intensive. For those who do machine learning regularly, it's about building pipelines and architectures. It has an infinite range of possibilities, ways to do this, and many ways we don't know. Oftentimes you have to just experiment and see if something works or not. And this also requires a lot of implicit knowledge that you cannot find in textbooks, because you first have to gather this this knowledge through experience. So the first step is you have to clean data, you have to preprocess that, featureize it, select the features, and so on. It's already a whole space of possibilities. Then you have to select the model. This model has high parameters, and if you choose something like deep learning, then you also have to design the architecture, which again has lots of possibilities. And oftentimes you want to take pre-trained models and start from there. That again has a whole range of possibilities and a whole range of questions. Right? So that's why it's so labor intensive. There's a lot of trial and error in figuring out what works and what doesn't. And it's a very oftentimes you can change something a little bit and it doesn't work at all anymore. Right? It's very sensitive to change. So can we automate this process? Second reason why we want to do this is to build robust automated systems in the future. Right? If you have robots on Mars, they lose contact and they have to figure out for themselves what to do, they would need something else. They cannot depend on humans to manually tell them what to do or manually upload a model, for instance. Okay, so the end goal the general goal, it's an evolving goal, of automated machine learning is to replace what's currently manual with automated search and smart techniques, right? So instead of needing a whole range of techniques, a large group of scientists who spend a lot of time with trial and error, let's allow a smarter team of scientists, give them an automated helper that they can give tasks, and then this helper will automatically search for the optimal models and then give them solutions back. And so they can interact with that and find good solutions. And ideally, this robot, has a memory. It remembers what it did in the past, right? And so as it sees more and more problems, it learns basically how to build machine learning models and help people better. So if you look at what drove progress in some fields of AI, you can see that people got a long way. Right? We learned a lot over the years how to build deep neural networks, but the last ones that really went beyond human performance were the ones where you have these AutoML techniques that fine-tune the networks and can explore many cases very fast. Of course, building on what the humans already discovered, right? They didn't discover this from scratch. They used the inventions that humans already did and put into the systems. And I also have to quantify this a bit that I think we're still currently at the pioneering stage of AI, where, like if you compare this to flight, we are now where it's culturally accepted to use AI, but it's not for everybody. Not everybody can easily use it, right? And we still need to make this final step to make it truly democratic. And so some things we need to solve are making these algorithms more efficient. Sometimes these algorithms, they use a lot of data, a lot of compute. Right? This is not sustainable. We need to make them more efficient, like humans are. They should adapt. They should continuously learn new tasks efficiently. And we need to think about things like safety, explainability, and fairness, and causality. Right? These are still largely unsolved. Okay, so how does AutoML work? AutoML basically first defines a search space of possible models that you want to search. Could be a pipeline, could be a neural network, could be a combination of both. It defines which are the operators, which are the kind of layers, which are the interconnections, and this together defines the search space. Right? And once you have done that, then the question is, okay, how do you search this vast space of possibilities for a good solution? And there's a whole lot of work here, which I won't go into today. So you can use evolution, gradient-based techniques, Bayesian optimization, reinforcement learning, and so on, to search this space efficiently, or efficiently as possible. And the last step, which we are currently only exploring, is meta-learning, because you want these techniques to get better over time. Currently, they still depend a lot of humans defining the optimal search space, and there's only so much we can do. And we hope in the future, meta-learning techniques can help us to learn how to do this more efficiently, to transfer information from previous tasks to new tasks. For instance, if you know that this task that you're given is similar to a previous task, as a human, you would, okay, I'll use that again, right? But a machine currently doesn't do that, or at least not efficiently. So you want these techniques to learn that, remember what works, what doesn't work, and use that efficiently. Okay, so, sorry. If you can do this, so say that we have this agent, which we're developing, we give it a lot of tasks, we let them find solutions, and it has a memory. It will remember over time and time what works, what doesn't work. And we can give these agents a lot of tasks, and they'll learn over time what works and doesn't work. And we can use OpenML here as our global memory. Right? We can store all this information online. Both humans and agents and AI systems have access to it because everything is machine readable. Right? And so say that you give it a new data set, what it can do, it can look at OpenML, which data sets are similar, which problems have people tackled before. It could look up what worked before, and it can use that to bootstrap the search for good new models that are ideal for your situation. And it's already being used by different systems. For instance, AutoScaleLearn is a tool that automatically builds pipelines in scikit-learn, and it uses OpenML to do the warm start. So if you get a problem, it looks, are there some ways that people have done before, which works well, and I'll start with that. If you use SageMaker or Amazon, it has a model that's trained on OpenML data to predict which are likely the best models that you can use. Microsoft has a similar system, also trained on OpenML data, to predict, to recommend basically which pipelines will work better than others. And within TUE, we have our own tool called Gamma, which evolves pipelines given input data set. And the really fun thing here is that since OpenML is accessible to both humans and machines, they're all on the same playing field. So this is, for instance, something we do in our machine learning classes. So all the colored dots are students. We let them look for optimal solutions to a given task. And then afterwards, we run the AutoML bots to see if they can beat the students. So far, not yet. That's interesting. But we also hope in the future that these AutoML bots will learn from the humans, and the humans will also learn from the AutoML bots. Right? If you want to know more, we have a book out. It's free. It's open source, open access. So if you want to know any more about these topics, feel free to read it. I want to thank. If you want to join us, you can. It's an open source community. We do hackathons several times a year. We have a foundation. If you want to work with us, we also have a spin-off at TUE. It's called PortML. So if you want to use OpenML in a company or a commercial situation, you can also contact Giorgio, for instance, to talk about that. Some pictures of the team that are working on OpenML. Some more people I wanted to highlight in particular. And these are people from industry and academia combined. Okay, that's it. If you have questions, I'll have to answer them. Thank you.
Thanks, Joaquin.
Thank you.
Any questions from the audience?
Thank you, Joaquin, for your nice presentation. There are a few interesting questions. Mm-hmm. So a question from Natalia here. how to learn data cleaning, since this is one of the most labor-intensive tasks?
Yeah, that's a very good question. And this is something that probably cannot be completely automated in the short term because it requires a lot of domain knowledge. So either we need to work towards semi-automated systems in where there's an automated system that basically gives suggestions to an expert that can then agree to accept or do something else. Or we should somehow include domain knowledge in these systems. But currently we don't really know yet how that works.
Okay, thank you. Then another question from Daan Hegger. How do you make sure the metrics of the uploaded models are relevant to a certain problem? I try to summarize a little bit more because it's quite a detailed question, but how important is the context of the data to determine its trustworthiness?
Okay. So the first question is, how do you define the optimal metric? So OpenML on purpose separates data from the task, right? Because sometimes people have different goals with the same data set, right? So that's why they're separate. So you can have a data set, and then you define, I want to build a classification model predicting this thing, and I want you to evaluate it on accuracy, for instance. So you can define it. So this it's different from a challenge where there's a fixed target. In this case, you can set any target you want, and you could create different tasks for the same data set. Also, we sort of saw this coming. So instead of evaluating only one evaluation metric, when we're evaluating models, we're evaluating like 50 of them, right? So we give them all the results back. So people can afterwards filter the data any way they want, right? So if there's 1,000 models being built, people can like sort them on recall, precision, F-measure, accuracy, whatever they want, what's most relevant for their field, right? So A, people can choose different tasks, and B, people can afterwards also rank them differently. The question about the trustworthiness of the data, okay, so there's a few things we can do. So what we do check for errors in the data, and as far this is a very moving field, a rapid moving field. We do check things like, are there obvious mistakes like typos and so on in the data that we can highlight? Can we encode the data in such a way that those typos do not matter anymore, for instance, right? Things like, there's something called like data diff. If you have data that evolves over time and suddenly like a sensor breaks, you can detect it, right? So you can also tell people this is true. So for now, the best we can do is sort of run these checks automatically. And we couldn't do that because the data is, again, uniformly formatted. So we only have to implement this once, and we can check all the data sets to see if there are particular issues. But yeah, there's still this human component that has to follow up on this. And also ethics, right? Ethics is also very important. That's something we cannot always easily detect.
Then I have a question from René van den Elzen. How to use the OpenML framework in a corporate environment?
That's a good question. So there's a few things you can do. You can either, because OpenML is open source, you can just download it and run it internally. There's a company called PortML, it's a spin-off at TUE, which also provides this as a service. That's one thing. So that's if you cannot share the data in any way, that's possibly the only thing you can do, right? You have to like wall it up. We can think of other things. We can think of sort of distributed networks of trusting companies, for instance, right? So that's completely perpendicular what the work that we're doing. But by making this openly available, we hope that people will use this in many different ways. And that if, for instance, different hospitals that want to share their data, allow them to basically have their own OpenML instances and then define a way to define the data that they can share, right? So it's largely unsolved, that question. And there's other things you can do as a company. You can, for instance, if you want to, the real power of OpenML is that the data is openly available to everybody. So if you put a data set on there, the AutoML bots will start running on it. People will start trying solutions for it, right? If you want to encourage that, you can try to find ways to make your data publicly available, or you can generate like synthetic data that's close enough for your interests, and that way also encourage the community.
Maybe a final question.
Sure.
A question from Daan Hegger. I think it's about auto-learning. Is there a risk of OpenML choosing the wrong previous problem, which leads into generating a faulty model that does not help to solve the problem?
That's a good one. Yeah, so that's a question of priors, right? Well, what we call the problem with priors. So having a prior, making assumption about what works and what doesn't work based on experience can massively increase speed. That's what we humans do. If we are given a task, we use our experience to solve a problem a given way. It can be that our experience is wrong, and we're doing the completely wrong thing. And the same is true with AI systems. And we know that sometimes priors are bad. We know, for instance, that, well, bad. We know, for instance, that the first AlphaGo systems were not really able to defeat humans at playing Go, but the later versions, well, Alpha 0, they had no prior. So the first games were trained on actual games that people did, and that gave them an edge, right? Because they had experience that they put into the system. But only when they basically said, let's do away with that and let the system just learn by itself, let it play games against itself, and that way it got better, right? Because it was not held back by these priors that humans basically put into the system. So it's a double-edged sword, right? So it can dramatically help you get solutions faster. It can also mean that you may not find some solutions.
All right, thanks. I think we can conclude that we have quite a bright audience with such intelligent questions, I would say.
Excellent, yeah, very much.
Well, thanks a lot, especially for flying solo in this duo talk. You did brilliantly. So thanks for your talk.
And thank you. Bye-bye.
So we will go to the final coffee break. This is a short one. So we will arrive back at 2:45, so 2:45. And well, we hope to see you then. And we will go to the final 2 duo talks for today. Hope to see you.